Okay, we are going to pick up with geometric models as we take a look at probability. Geometric models are going to tell us a little bit different information than before. So we're going to have the same assumptions as we did. It's a Bernoulli situation. So our trials have to be independent of each other. That means one trial does not impact the next one at all. Our success and failure are our only possible outcomes, and I would add to that that the probability of success or failure must remain constant. So a constant probability of success or failure. If the successes are changing their chances over time, then we can't do this with a geometric model. A geometric model is going to tell us how long it takes to get a success from a Bernoulli situation. So if we have this success or fail, like how many tries does it take until we get that first success? So a geometric model, now I have used the letter R here to represent the number of tries. That may or may not make sense, but whatever, the letter doesn't really matter. So this is basically going to give us, this is our geometric model, it's going to give us how many, or the probability of a success after R number of tries. And again, we have here expected value, variance, and standard deviation formulas. And for each model, these are slightly different. So our expected value, mu, is going to be 1 divided by the chance of success. Our variance is going to be Q divided by success squared. And of course, our standard deviation is the square root of the variance. So let's take a look and try this. So a cereal company puts out a sports card in every cereal box, and the chance of getting a Pete Sampras card, and if you don't know who he is, he's an old famous tennis player, tennis pro, but the chance is 20%. So what is the chance of finding a Sampras card on the third cereal box? So this kind of assumes that on the first cereal box and the second cereal box that you hadn't actually gotten one. So we're going to use P times Q to the R minus 1, and R is going to be 3, so it's the third try. So we're going to do 0.2 times, now Q is failure. So P is 20% success rate, well then Q is an 80% fail rate. So 0.8 is our failures. So we have 3 tries, so R minus 1, 3 minus 1 is 2. And we'll pop that into the calculator and see what we get. Just give me a second. All right, and I get on this one 0.128, so 12.8% chance that the third, it takes 3 tries to get a success. Part B. How many cereal boxes can you expect to eat before you find the Sampras card? So our expected value is 1 over P. So 1 divided by 0.2. So that is going to be 5. So 5 times. All right, so if our email is mostly spam, in fact, 82% spam, let's answer a few questions. So what is the probability that a message is real and not spam? So in this case, because I'm talking about in all these about the real message, I really don't want to talk about the spam. So I'm going to say that a failure is going to be 0.82. And I'm going to say that a success, so that's Q, and I'm going to say that a success is going to be 0.18, and I get that by 100% minus 82%. And the only reason I'm doing that is because each of these questions really is asking about, talking about getting a real message versus a spam message. So what is the probability that a message is real and not spam? Well, 18%. What is the chance that the first real message is the fourth one? So in other words, I have to open 4 emails before I get a real message. So that's going to be this PQ to the R minus 1. So R being 4, we're going to do 0.18 times 0.82 to the 4 minus 1, so to the 3. So we would put in our calculator 0.18 times 0.82 to the third. And I'll go ahead and type that in, hopefully correctly. And I get 0.099. So 9.9% chance that it takes 4 tries to get a real email. How many emails do you need to open before you can expect to get or to find a real message? So mu is going to be 1 over p. So mu is 1 divided by 0.18. So mu, our expected value, the expected number of tries that it's going to take, is 5.55 repeated. So 6 tries. We'll say 6 tries. And then this last question is at the very bottom here. What is the variance and standard deviation? And just to kind of put in there so that we have gone over it, our variance is going to be Q over P squared. So in this case, 0.82 divided by 0.18 squared. And I'll go ahead and put that in as well. And this is from the perspective, of course, that a success is going to be getting a real message, not that a success is getting a spam message. And anyway, for my variance, I get 25.3, which means for my standard deviation, now this was variance, so that should have been squared right there. Our standard deviation is going to be the square root of 25.3, which I'm just going to say is about 5. That's good enough. Just double check here. And yeah, well, I think maybe the last question. Let me check real quick. Yes. So the last question that we'll go over, you're running a blood drive. 6% of donors are O negative. This is universal. Universal as in anyone who donates it. That's very good because it can be transfused into anyone. So let's say tons of people have come, so we have lots of people donating. The number that are donated really doesn't matter. What is the chance that the last of 10 people is O negative? So we have 10 people in line, and what's the chance that it takes us the 10th person to actually get a success here? So success is going to be 6%, so 0.06, which means a failure is 0.94. So our probability of that last person is going to be 0.06 times 0.94, and this is going to be R is my 10, so 10 tries, so to the 9, because this is R minus 1. So we'll put this in, and I get 0.0344, so 3.4% chance that the 10th person has O negative. How many people would have to donate before you can expect to have an O negative? So mu is going to be 1 divided by P. So in this case, 1 divided by 0.06. So mu is going to be, type that in, 16.67. So about 17 people you would have to donate before you get an O negative. And again, asking what is the variance and standard deviation. So our variance is going to be Q over P squared from our formulas from at the beginning. So that's going to be 0.94 over 0.06 squared. And just give me a second to type that in. And I get 261.1. And our standard deviation is going to be the square root of that. So I'll go ahead and square root that. And I get 16.2 about. All right, so that wraps up the geometric models. And just to rehash our geometric, like I'll put it up here, we have PQ to the R minus 1. Our mean is going to be 1 over P, and our variance is going to be Q over P squared. And of course, our standard deviation is the square root of that, square root of the whole thing. All right, good luck.